Tonight, we're going to look at the rules the universe actually runs on. The ones hiding underneath everything you can see, touch, and measure. Quantum mechanics. The name makes it sound like something only physicists need to worry about. Abstract, remote, sealed off from ordinary life behind a wall of mathematics. But here's what's going to change how you think about the world around you. Every atom in your body, every photon that has ever reached your eyes, every chemical reaction keeping you alive right now, all of it runs on these rules. Rules nobody expected to find. Rules so strange that the physicists who discovered them spent decades arguing about what they actually meant. By the end of tonight, you're going to understand not just what quantum mechanics says, but why it works the way it does, and what it reveals about the true nature of reality. Before we begin, if you enjoy these topics as much as we do, make sure to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with the world as you know it. You drop a ball from your hand, and it falls. Every single time. Under the same conditions, the ball falls to the floor at the same rate, takes the same path, hits the same spot. The universe at human scale is predictable. Give a physicist the starting position and velocity of any object, and they can tell you exactly where it will be at any future moment. Newton figured this out in the 17th century. It forms the backbone of classical mechanics, the physics of everyday life. The physics that put spacecraft in orbit, built bridges, calculated the trajectory of cannonballs, sent the Voyager probes on precise courses through the outer solar system, and let engineers design every machine you've ever used with exact confidence about what it will do. Classical mechanics works. Beautifully, precisely, reliably. The universe at human scale obeys deterministic laws, and those laws have been known for over 300 years. Nothing about a ball falling from your hand is mysterious. Now go smaller, vastly smaller, down to the scale of atoms and electrons and photons and the fundamental particles that make up everything you've ever seen or touched or breathed. And the rules change completely. The ball doesn't just fall anymore. At the quantum scale, the ball exists in a superposition of falling and not falling until you look at it. The path isn't determined in advance. The outcome isn't set until it happens. And when you measure it, the very act of measuring changes what you're measuring. This isn't philosophy. It isn't metaphor. It's what the equations say, and what decades of experiments confirm with extraordinary precision. Quantum mechanics is the most precisely tested theory in the history of science. Its predictions match experimental results to 11 decimal places. No other theory in physics comes close. And what it says about reality is that, at the most fundamental level, the universe is not deterministic. It is probabilistic. Not because we lack information, not because our instruments are imprecise, but because that's how nature actually works. That conclusion took decades to accept and is still, in a deep sense, philosophically unresolved. Even now, even after all the experiments, even after building entire industries on top of it. To understand how we got here, you need to go back to the late 1800s. Physics at that point was in a state that felt like completion. Newton's mechanics handled everything that moved. Maxwell's equations described electricity and magnetism and predicted electromagnetic waves, including light, with astonishing precision. Thermodynamics explained heat and energy. The known forces fit together into a coherent picture. A few prominent physicists actually suggested the big questions had been answered. That physics was essentially done. What remained was just filling in details, measuring known quantities more precisely, applying established principles to new situations. Lord Kelvin, one of the most respected physicists in the world at the time, reportedly described the future of physics as involving only more decimal places. He was wrong in the most spectacular way imaginable. Then things started not working. The first crack appeared in something called blackbody radiation. A blackbody is an idealized object that absorbs all electromagnetic radiation that hits it and emits radiation based purely on its temperature. Real objects approximate this behavior, and heated metal is one of the better examples. When you heat iron, it first glows a dull red, then orange, then yellow-white as the temperature rises. The color tells you about the temperature. Classical physics had an equation for this relationship, the Rayleigh-Jeans law, derived from well-established principles of thermodynamics and electromagnetism, and when physicists tested it against measurements of actual glowing objects, it worked beautifully at long wavelengths, at the red and infrared end of the spectrum. But at short wavelengths, at the ultraviolet end, the classical prediction went completely wrong. It didn't just disagree with measurements by a small factor. It predicted infinite energy emission at short wavelengths. Infinite. A glowing piece of metal, according to classical physics, should have been emitting an infinite amount of energy in the ultraviolet and beyond, which is obviously not what happens. The classical prediction was so badly wrong at short wavelengths that physicists called it the ultraviolet catastrophe, a friendly name for a deeply embarrassing theoretical failure. In 1900, a German physicist named Max Planck found a mathematical fix. He discovered that if you assumed energy wasn't continuous, if you assumed that light was emitted not in smooth flowing amounts but in discrete little packets, then the math worked. The predictions matched the observations perfectly, across the entire spectrum. The ultraviolet catastrophe disappeared. Planck called these packets quanta, from the Latin for how much. Each quantum of light carried an amount of energy proportional to the light's frequency. High-frequency light, more energy per quantum. Low-frequency light, less energy per quantum. The constant of proportionality he introduced, now called Planck's constant, is one of the most fundamental numbers in all of physics. Planck wasn't entirely sure what the quanta meant physically. He thought of them as a mathematical trick, a clever device to make the equations behave. The idea that energy had to be discrete, that it came in indivisible chunks rather than flowing continuously like water, struck even Planck himself as strange. He spent years trying to fit the result back into a classical framework where it wouldn't be necessary. He couldn't. The equations kept insisting that the trick was real. 5 years later, in 1905, Albert Einstein took Planck's idea further. He proposed that light wasn't just emitted in discrete packets. It actually was discrete packets. Light, which everyone knew was a wave, which had been shown to be a wave, which produced wave phenomena like interference and diffraction that were unambiguous signatures of wave behavior, was also made of particles. Einstein used this idea to explain something called the photoelectric effect, where shining light on certain metals causes them to emit electrons. Classical wave theory said that if you shone dim light on a metal long enough, the electrons would eventually accumulate enough energy to escape. Brighter light just meant more energy arriving faster. Given enough time, any frequency should work. But that's not what happened. Instead, whether electrons were ejected depended entirely on the frequency of the light, not the brightness. High-frequency light, even very dim, could knock electrons loose immediately. Low-frequency light, even blindingly bright and shining for extended periods, could not knock electrons loose at all. Einstein's particle picture of light explained this immediately. Each particle of light, which we now call a photon, carries an amount of energy determined by its frequency. High frequency means high energy per photon. Low frequency means low energy per photon. If one photon doesn't carry enough energy, no number of photons arriving slowly will eject an electron, because electrons need a single photon with enough energy, not a slow accumulation. The explanation worked. The photon was real. Einstein won the Nobel Prize in Physics in 1921 for this work, not, as many people assume, for relativity. But this created a problem that no one had a clean answer to. Light was a wave. The wave nature of light was not in doubt. Experiments going back to Thomas Young's double-slit experiment in 1801 had shown conclusively that light interfered with itself in the way waves do. When Young shone light through two narrow slits, the pattern on the screen behind wasn't two bright bands. It was an alternating pattern of bright and dark stripes. The signature of waves from the two slits overlapping and adding together or cancelling out, depending on whether the peaks aligned or opposed. That pattern was definitive. Light was a wave, and now light was also a particle. Both at the same time, not one or the other, depending on the situation. Both, always, with the nature you observed, depending on how you looked. This is wave-particle duality, and it was the first sign that something deeply strange was going on. The nature of something at the quantum level is not fixed and independent of how you choose to examine it. That idea would only get stranger. The strangeness deepened through the 1910s and 1920s. Physicists were working to understand the structure of atoms, which experiments had begun to reveal with increasing clarity. In 1911, Ernest Rutherford showed that atoms were mostly empty space, with a tiny, dense, positively charged nucleus at the center and much lighter, negatively charged electrons somewhere in the surrounding space. The classical picture that emerged was a miniature solar system, the nucleus at the center, like the sun, electrons orbiting it at various distances like planets. It was a satisfying image, intuitive, orderly, and completely wrong. An electron orbiting a nucleus is an accelerating charge, and classical electrodynamics is absolutely clear on what accelerating charges do. They radiate energy in the form of electromagnetic waves, continuously. So the orbiting electron should continuously lose energy, spiraling inward as it radiates, and crash into the nucleus in a fraction of a second. The math said an electron would spiral into the nucleus in about 10 to the negative 11 seconds, about 100 picoseconds, a tenth of a nanosecond. Atoms shouldn't be stable, but they obviously are. Everything around you is made of atoms that have been stable for billions of years. Your body is made of atoms that formed in stellar explosions billions of years ago, drifted through interstellar space, condensed into the sun's nebula, found their way into Earth, and eventually assembled into molecules that eventually assembled into you. All of that required stable atoms. The classical picture was simply wrong. In 1913, Danish physicist Niels Bohr proposed a model in which electrons could only occupy certain specific orbits, defined by discrete energy levels. An electron in a permitted orbit didn't radiate. The classical rule about radiating charges simply didn't apply. When an electron jumped from a higher orbit to a lower one, it emitted a photon with exactly the energy equal to the difference between the two levels. When it absorbed a photon of exactly the right energy, it jumped up. This explained the discrete spectral lines that had been observed when elements like hydrogen were heated and their light passed through a prism. Hydrogen didn't emit a continuous rainbow of light. It emitted specific colors at specific wavelengths, corresponding to the specific energy jumps in Bohr's model. The model worked for hydrogen. Precisely. The predicted wavelengths matched the observed spectral lines with high accuracy. But Bohr's rules were somewhat arbitrary. He imposed them on the equations without fully deriving them from any deeper principle. Why those orbits? Why not others? Why were only certain distances from the nucleus permitted? Bohr had no answer rooted in physics. He had a rule that worked. That was unsatisfying, and everyone knew it. The answers came from a young French physicist named Louis de Broglie. In his doctoral thesis in 1924, de Broglie proposed something audacious. If light, which was known to be a wave, also behaved like a particle, maybe particles, which were known to be particles, also behaved like waves. Maybe everything had a wave nature. Not just photons, electrons, protons, atoms, every massive particle in the universe. The wavelength he predicted for a particle was equal to Planck's constant divided by the particle's momentum. The idea was so strange that de Broglie's thesis committee wasn't sure what to do with it. They sent it to Einstein, who confirmed it was brilliant, and it was testable. If electrons had wave properties, they should show interference, the hallmark of waves. In 1927, Clinton Davison and Lester Germer at Bell Labs in New Jersey showed exactly that. Electrons fired at a crystal lattice produced an interference pattern. Not two clusters from bouncing off two different atoms. An interference pattern with alternating bands of high and low electron density, exactly like the light bands Young had observed over a century earlier. Exactly what you'd expect from waves passing through the regular spacing of a crystal. Electrons were waves. Or rather, like light. They were both. De Broglie's idea was confirmed, and it answered Bohr's question about permitted orbits. The allowed electron orbits were the ones where the electron's wave nature fit perfectly around the nucleus, forming a standing wave. Think of a guitar string. The string can vibrate at specific resonant frequencies, the ones where the wave fits cleanly between the two fixed ends. Those are the harmonics. Any other frequency doesn't produce a sustained standing wave. Similarly, only the electron orbits where the de Broglie wavelength fitted an exact whole number of times around the circumference of the orbit were allowed. Those were the stable orbits. The ones where the electron wave resonated. The quantum nature of atoms wasn't arbitrary. It was geometry. Wave geometry on an impossibly small scale. And it explained, from first principles, why atoms were stable. A standing wave, by definition, isn't going anywhere. The electron isn't radiating because it isn't, in any meaningful classical sense, accelerating in a circle anymore. It's a standing wave of probability amplitude wrapped around the nucleus. The classical objection didn't apply to a standing wave. The problem dissolved. What came next was the mathematical framework that pulled all of this together. In 1925 and 1926, the formal equations of quantum mechanics were developed. Werner Heisenberg, working in Germany, arrived at one version. using a formalism based on matrices, arrays of numbers that combined in specific mathematical ways. His approach was abstract and hard to visualize. It didn't give you a picture of what an atom looked like. It gave you a set of rules for calculating what you'd measure. Erwin Schrödinger, an Austrian physicist working in Zurich, arrived at another version independently. He was inspired by de Broglie's matter waves. If particles had wave natures, Schrödinger reasoned, there should be a wave equation describing them. Something like the equations already known for sound waves and light waves. He found one. Schrödinger's equation described how a mathematical object he called the wave function evolved over time. The two approaches, Heisenberg's matrices and Schrödinger's waves, looked completely different and used entirely different mathematics. They gave the same answers. British physicist Paul Dirac later showed they were mathematically equivalent, two different ways of writing the same underlying theory. The central object in Schrödinger's formulation is the wave function, typically written with the Greek letter psi. The wave function is a mathematical description of a quantum system. It encodes everything that can be known about a particle, including its position, momentum, energy, and other properties. But here's what makes it strange. The wave function doesn't tell you where the particle is. It tells you the probability of finding it in any given location if you measure. Before measurement, the particle doesn't have a definite position. It has a spread of possible positions, each with an associated probability. The wave function describes all of them simultaneously. This is superposition. A particle in superposition isn't in one place or another place. It's in all its possible places at once, with different probabilities for each. And this is not a statement about our ignorance. It's not that the particle is really at some specific place and we just don't know where. The particle genuinely doesn't have a definite position until it's measured. The wave function is the complete description of reality, and reality at the quantum level is fundamentally probabilistic. To calculate what you'll observe, you take the wave function and square its amplitude at each point. That gives you the probability distribution, the likelihood of finding the particle at each location. The particle is most likely where the wave function is largest in magnitude, least likely where it's small. When you make a measurement, you get one definite result, not a spread of probabilities. One outcome. After the measurement, the wave function changes. It collapses. The spread of possibilities collapses to the single outcome you observed. This is called wave function collapse, and it's one of the most debated ideas in all of physics. Something happens when you measure a quantum system. The measurement doesn't just reveal a pre-existing value. It brings a definite value into existence. The question of what exactly happens during measurement and what it means physically is called the measurement problem. It is not solved. Despite nearly 100 years of debate, physicists still disagree about what wave function collapse actually is. Schrödinger's equation tells you how the wave function evolves over time when you're not measuring. It's a smooth, continuous, perfectly deterministic evolution. Given a wave function at one time, the equation tells you exactly what it will be at any later time. No randomness, no probabilities. Just smooth mathematical evolution, as lawful and predictable as Newton's equations. But then you measure, and suddenly you get a random outcome drawn from the probability distribution. The transition between those two processes, smooth deterministic evolution and random probabilistic collapse, is the heart of the measurement problem. Nothing in Schrödinger's equation explains why measurement is different from any other physical process. the equation doesn't even contain the concept of measurement. From a mathematical standpoint, your detector is also a quantum system, governed by the same equations. Your eyes are a quantum system. Your brain is a quantum system. If everything is quantum, what makes measurement special? Why does the act of observing cause collapse? Different interpretations of quantum mechanics answer this question differently, or avoid it in different ways. The Copenhagen interpretation, developed primarily by Niels Bohr and Werner Heisenberg in the late 1920s, is the oldest and most commonly taught. It says, essentially, don't ask. The wave function is a tool for calculating probabilities. When you measure, you get an outcome. The wave function updates. Questions about what's really happening between measurements are outside the scope of physics. The theory works. Use it. Stop asking what it means. Bohr's version of this was even more radical. He argued that quantum mechanics wasn't a description of reality at all. It was a description of our knowledge of systems, a framework for predicting what we would observe. The question of what electrons are doing when we're not looking was, in his view, meaningless. Physics could only talk about what we could measure. This position made Einstein deeply uncomfortable. He famously objected with a question that became one of the most quoted lines in the history of physics. He asked whether the moon exists when no one is looking. The Copenhagen answer, in its strict form, is that the question has no scientific content. Einstein never accepted this. He believed physics was a description of an objective reality that existed independent of observers. He spent years trying to prove quantum mechanics was incomplete, that there was a deeper deterministic theory underneath the probabilistic surface. He didn't succeed. The experiments continued to match the quantum predictions. Every time, with impossible precision. Schrödinger himself was deeply unsatisfied with the Copenhagen interpretation. He devised a thought experiment to show how strange its implications were. Imagine a cat in a sealed box. Inside the box is a mechanism connected to a radioactive atom. If the atom decays, the mechanism is triggered and releases something that ends the cat. If the atom doesn't decay, nothing happens. The cat remains fine. Radioactive decay is a quantum process. Before you open the box to look, the atom is in a superposition of decayed and not decayed. According to Copenhagen, the wave function describes what we can know, and until measurement, both states exist simultaneously. By this logic, the cat would be in a superposition of two states until the box is opened and someone looks. Schrödinger didn't intend this as a cute story about a cat. He intended it as a demonstration that something about the Copenhagen interpretation must be wrong. Superpositions of microscopic quantum states shouldn't propagate upward and leave macroscopic objects in states with no classical description. The thought experiment is called Schrödinger's cat, and it became one of the most iconic illustrations in all of science. The problem it illustrates is not resolved. The cat remains, in a very specific sense, the reason physicists still argue at conferences. The most direct attack on the question of whether quantum mechanics was complete came in 1935. Einstein, along with Boris Podolsky and Nathan Rosen, published a paper describing a scenario they believed demonstrated a fatal flaw in the theory. The paper is known today by the initials of its authors, the EPR paper. The scenario involved what we now call entanglement. Two particles interact in a way that correlates their quantum states. Then they're separated. According to quantum mechanics, neither particle has a definite value for certain properties, like spin, until it's measured. When you measure one particle and find its spin pointing up, you instantly know the spin of the other particle is pointing down, regardless of the distance between them. Einstein, Podolsky, and Rosen argued this proved quantum mechanics was incomplete. For the correlation to be real without violating relativity's prohibition on faster-than-light influences, the particles must carry hidden information from the start, predetermining their outcomes. If particle A already knew it would be measured spin up, and particle B already knew it would be measured spin down, no spooky action was required. They just had pre-existing values. Einstein called any alternative spooky action at a distance and considered it physically impossible. His conclusion was that quantum mechanics was missing something. There had to be hidden variables, predetermined outcomes encoded in the particles that the quantum description simply failed to capture. For nearly 30 years, this remained a philosophical debate. No one could test it. Then, in 1964, physicist John Bell derived a remarkable result. He showed that if hidden variable theories of a certain type were true, the correlations between entangled particles would obey certain mathematical inequalities. The inequalities set a precise limit on how strongly correlated the outcomes could be if the particles were just carrying predetermined information. Quantum mechanics predicted stronger correlations than the inequalities allowed. You could test this experimentally. Through the 1970s and 80s, physicists ran increasingly careful experiments. The most definitive early results came from Alain Aspect and his team in Paris in 1982. Their experiments showed correlations between entangled photons that violated Bell's inequalities by a wide margin. The particles were correlated more strongly than any hidden variable theory could explain. Quantum mechanics was right. Hidden variables of the kind Einstein imagined didn't exist. Subsequent experiments closed loopholes one by one. Perhaps the detectors weren't recording all the particles, and a biased sample was making it look like a violation. Fixed. Perhaps the choice of what to measure on one particle could be influenced by the setting of the other detector, allowing a subtle local communication. Fixed. By the 2010s, experiments were being performed where the measurement settings were chosen randomly at the last possible moment, while the particles were in flight, using random number generators separated by enough distance that no signal could travel between them in time. Bell's inequalities still violated. Every time. In 2022, Alain Aspect, John Clauser, and Anton Zeilinger were awarded the Nobel Prize in Physics for their experimental work on entanglement and Bell inequality violations. The prize arrived nearly 60 years after Bell's theorem and nearly 90 years after Einstein's original challenge. And the answer was unambiguous. Einstein was wrong about hidden variables. The universe is genuinely non-local in the way quantum mechanics implies. Entangled particles really are correlated in ways that can't be explained by anything they carry locally. The spooky action is real. It just doesn't allow you to send information faster than light, because the individual outcomes are still random. You can't choose what result you get. You can only discover that whatever you got, the other particle got the corresponding result. The universe is doing something with entangled particles that has no classical analog. The correlation is built into the quantum state, not into hidden properties of the particles themselves. In 1957, a young American physicist named Hugh Everett III proposed a radically different interpretation. He argued that wave function collapse never actually happens. Schrödinger's equation always holds. It always evolves smoothly and deterministically. When a measurement happens, the observer doesn't force the quantum system to pick one outcome. Instead, both outcomes occur. The universe branches. In one branch, the particle was measured, spin up. In the other branch, it was measured, spin down. Both branches are equally real. Both contain a version of the observer who just made the measurement. Both versions believe they're in the only universe. This is the many worlds interpretation. It avoids the measurement problem entirely by refusing to accept that measurement is special. Measurement is just another physical interaction, and Schrödinger's equation handles it like any other. The price you pay is enormous. Every quantum event that could have multiple outcomes generates multiple branches. Every radioactive decay, every photon interaction, every electron jumping between energy levels. The number of branches is incomprehensibly large, grows constantly, has always been growing since the beginning of time. Everett submitted his thesis to Bohr and the Copenhagen establishment and was largely ignored. He left academic physics shortly after. His interpretation was rediscovered and popularized decades later, primarily by physicist Bryce DeWitt, and it's now one of the most seriously discussed alternatives to Copenhagen. It solves the measurement problem cleanly. It takes quantum mechanics at face value. It doesn't add any new rules. It doesn't invoke observers as special. But it implies that reality consists of a stupefying number of parallel branches, all equally real, none of which can communicate with or observe each other. Many physicists find this too extravagant. If all those branches exist, how do we get the right probability rule from them? Why do the probabilities match Schrödinger's squared amplitude rule instead of just being equal for every branch? This is called the probability problem for many worlds, and it hasn't been fully resolved. Others think many worlds is the most honest reading of the mathematics. The debate continues. Another interpretation, associated with work by David Bohm and developed further in the 1950s, takes yet a different approach. It says quantum mechanics does have hidden variables, just not the local kind Einstein imagined. In Bohmian mechanics, particles have definite positions at all times. They're guided by a quantum potential, a real physical field that encodes all the wave information. The particle is always somewhere definite. The wave function doesn't collapse. It always fully exists, guiding the particle's motion through a deterministic path. The apparent randomness of quantum outcomes comes from our ignorance of the particle's precise initial position, not from any fundamental indeterminacy in nature. Bohmian mechanics reproduces all the predictions of standard quantum mechanics. Every experiment gives the same result. It's non-local, which Bell's theorem shows any hidden variable theory has to be, since locality is what the experiments ruled out. And it's deeply unfamiliar in other ways. The quantum potential acts instantaneously across space. The wave function for a many-particle system lives in a configuration space with many more dimensions than ordinary three-dimensional space. It's a consistent interpretation. Most physicists don't use it, partly for reasons of elegance, partly because it adds structure that's difficult to generalize to the relativistic quantum field theories that describe particle physics. But it exists, and it proves that a deterministic account of quantum phenomena is possible at the cost of accepting non-locality. There's no consensus on which interpretation is correct. This isn't like most questions in physics, where the debate settled decades ago. Interpretations of quantum mechanics remain genuinely contested among serious physicists. What everyone agrees on is the formalism, the equations, the predictions. What everyone disagrees on is what those equations mean about the nature of reality. That's a strange situation for a mature scientific theory. But quantum mechanics is a strange theory. One of the consequences that follows directly from the wave function picture is something Werner Heisenberg identified in 1927. It's called the uncertainty principle, and it is one of the most misunderstood ideas in all of science. The common version says you can't know both the position and momentum of a particle at the same time. That's approximately right. But the reason is usually wrong. The popular explanation says this uncertainty comes from the act of measurement disturbing the particle. If you want to locate an electron precisely, you have to bounce a photon off it. But that photon kicks the electron, changing its momentum. So measuring position disturbs momentum. This is called the observer effect, and it's real. But it's not what Heisenberg's principle is actually about. Heisenberg's uncertainty principle is deeper than measurement disturbance. It's not about measurement disturbing the system. It's about what quantum systems actually have before you measure them. The position and momentum of a particle aren't just unknown to us. They're genuinely indeterminate. The particle doesn't have a precise position and a precise momentum simultaneously. It can't. Not because of any limitation in our instruments, because of what it means to be a quantum object. The mathematical reason comes back to waves. To specify a wave's precise location, you need a very sharply peaked wave packet. But a sharply peaked wave packet is built from combining many different wavelengths, many different components, each with a different frequency, and therefore, in quantum mechanics, a different momentum. The more precisely you define position, the more wavelengths you mix, the more spread out the momentum becomes. To have a very precise momentum, you need a nearly pure single wavelength. But a pure sine wave of one single wavelength extends infinitely in all directions. It has no definite position at all. It's everywhere. Position and momentum are complementary. Pinning down, one forces the other to spread. This is encoded in Heisenberg's inequality. The product of the uncertainty in position and the uncertainty in momentum is always greater than or equal to Planck's constant divided by 4 pi. Planck's constant is a very small number, about 6.6, 3 times 10 to the negative 34 joule-seconds. This is why you don't notice quantum uncertainty in daily life. For macroscopic objects, the uncertainties are fantastically smaller than anything measurable. A ball has a perfectly definite position and momentum for all practical purposes. For an electron, the uncertainties are large enough to completely dominate its behavior. The electron doesn't have a location in any classical sense. It has a probability cloud, a distribution of where it might be found, and that distribution is the reality. There's a related uncertainty principle between energy and time. The more precisely you want to know the energy of a quantum system, the longer you have to observe it. A quantum state that exists for only a very short time has an inherently uncertain, spread-out energy. This energy-time uncertainty has real physical consequences. It's why excited atomic states have a natural line width a spread in the frequency of light they emit, determined by how long the excited state lives before the electron drops back down. It's related to why virtual particles in quantum field theory are allowed to exist temporarily without violating energy conservation. It's part of why the vacuum itself has energy. The uncertainty principle is not a limitation on our measurements. It's a statement about what quantum reality actually contains. Before going deeper into the quantum vacuum, there's one more quantum property that needs its own moment: spin. In the early 1920s, experiments showed that electrons behaved in magnetic fields as if they were tiny spinning magnets. The obvious interpretation was that the electron was literally spinning, like a tiny ball rotating on an axis, creating a magnetic field the way a spinning charged sphere would. This picture is wrong. Not approximately wrong, completely wrong. The electron has no detectable size at current experimental limits. It's treated as a point particle. A point particle can't rotate in any meaningful classical sense. And if you calculate the speed at which the electron's surface would have to move to produce the observed magnetic moment, assuming even a very small radius, you get speeds faster than light, which is impossible. Electron spin is not a rotation. It's an intrinsic quantum property, a kind of internal angular momentum that has no classical analog whatsoever. It doesn't correspond to anything in everyday experience. It just exists. The spin of an electron can be measured along any axis you choose. When you measure it, you always get one of exactly two values, plus 1/2 or minus 1/2, in units of Planck's constant divided by 2 pi. Spin up or spin down. Not a continuous range, not some other value. Always one of exactly two. This is one of the starkest examples of quantization, of the discrete nature of the quantum world. The spin doesn't have a definite orientation before you measure it. Before measurement, the electron exists in a superposition of spin states. When you choose an axis and measure, you get spin up or spin down, with probabilities that depend on the superposition. And here's something even stranger. If you've just measured spin along the vertical axis and found spin up, then you immediately measure spin along the horizontal axis. You'll find either spin left or spin right with equal probability. The spin-up measurement didn't fix the horizontal component. Every new axis you measure is still probabilistic. The definite result you got on the first measurement only applies to that measurement along that particular axis. Measuring on any different axis is a fresh, probabilistic event. This is profoundly different from anything in classical physics. A classical spinning object has a definite angular momentum vector pointing in some direction. Measuring it along any axis just gives you the projection of that vector. Definite. Determined by the object's actual spin. Quantum spin has no such underlying vector. There is no definite direction before measurement. Spin is also at the heart of the fact that quantum particles come in two fundamental categories: fermions with half-integer spin and bosons with integer spin. The spin statistics connection, one of the deepest results in quantum field theory, links the spin of a particle to its statistical behavior. Particles with half-integer spin are fermions and must obey the Pauli exclusion principle. Particles with integer spin are bosons and can all pile into the same quantum state. This connection isn't an assumption, it's a theorem. It follows necessarily from the requirements of combining special relativity with quantum mechanics. The two ideas together, relativity and quantum theory, force the universe to organize its particles into two fundamental types, with the statistical properties they're observed to have. Spin also has direct practical importance. Nuclear magnetic resonance, the phenomenon underlying MRI machines, is based on the spin of atomic nuclei. Protons have spin, just like electrons. In a magnetic field, spin states have slightly different energies. Radio waves of exactly the right frequency can flip the spin from one state to another. When the spin flips back, it emits a detectable signal. By mapping where in the body these signals come from, an MRI machine creates a three-dimensional image of the internal structure. Every MRI scan ever taken, every tumor found, every stroke caught early because of an MRI, was possible because quantum mechanics says atomic nuclei have intrinsic spin that has no classical analog. Speaking of the vacuum, quantum mechanics says something very strange about empty space. Nothing, in the quantum mechanical sense, is not actually empty. The vacuum of space is not the absence of everything. It's a quantum state, the lowest energy state of every quantum field. And it's not zero energy. The vacuum has a ground state energy, sometimes called the zero-point energy. This emerges directly from the uncertainty principle. If a particle were perfectly at rest with zero momentum and perfectly localized in one place, both its position and momentum would be exactly known simultaneously. The uncertainty principle says this is impossible. Particles in their ground states can't stop moving entirely. They have to maintain some minimum jittering, some residual quantum motion, even at the lowest possible energy. This zero-point motion contributes energy to the vacuum, and quantum field theory extends this to fields. Every quantum field permeates all of space. Each has its own ground state, its own vacuum fluctuations. The vacuum isn't empty. It's seething with quantum activity. Fluctuations appearing and disappearing on timescales too short to observe directly. Virtual particles popping in and out of existence, briefly borrowing energy from the vacuum before giving it back. This sounds speculative. It isn't. The vacuum fluctuations have measurable physical effects. One of them was predicted by Dutch physicist Hendrik Casimir in 1948. If you place two flat conducting plates very close together in a vacuum, the quantum fluctuations between the plates are restricted. Only wavelengths that fit neatly between the plates can exist in the narrow gap. Outside the plates, in open space, all wavelengths are present. This creates a pressure imbalance. The fluctuations outside push inward more strongly than the restricted fluctuations inside push outward. The plates attract each other with a force that depends on their separation. This is the Casimir effect. It was first measured experimentally in 1997 by Steve Lamoureux at Los Alamos, confirming that vacuum fluctuations are real and physically significant. You can measure the force of nothing, quantum nothing, which turns out not to be nothing at all. Another measurable consequence of vacuum fluctuations is called the Lamb shift. In 1947, American physicist Willis Lamb measured the energy levels of hydrogen with extreme precision and found a small but definite difference between two levels that the Dirac equation, the relativistic quantum theory from 1928, predicted to be identical. The two levels were called the 2s1/2 and 2p1/2 states of hydrogen. Dirac's equation said they should have the same energy. Lamb measured a difference of about 1057 megahertz. Small, but precisely real and precisely measured. The explanation came from quantum electrodynamics. Vacuum fluctuations of the electromagnetic field cause the electron to jitter constantly in its position around the nucleus. This jittering shifts the electron's energy levels by tiny amounts, different for the 2s and 2p states, because of how those wave functions are distributed around the nucleus. When the calculation was done correctly in quantum electrodynamics, the predicted Lamb shift matched the measured value to an accuracy of parts per million. The vacuum interacts with matter. It shifts energy levels. It exerts forces. It's as real and physically consequential as any other field in nature. Understanding quantum mechanics at a deeper level requires going beyond particles to fields. Quantum mechanics, as originally formulated, described particles. But Einstein's special relativity created a problem. Relativity said that mass and energy were interchangeable. According to the equation E equals mc squared, this meant particles could be created and annihilated. A photon with enough energy could create an electron and its antiparticle, a positron. An electron and a positron could annihilate into photons. The number of particles wasn't conserved. Standard quantum mechanics, built around a fixed number of particles, each described by a wave function, couldn't handle this. A more general framework was needed. In the late 1920s and through the 1930s, physicists developed quantum field theory. The basic idea is that particles aren't fundamental objects. Fields are fundamental. Every type of particle corresponds to a quantum field that permeates all of space. Electrons are excitations of the electron field. Photons are excitations of the electromagnetic field. Quarks are excitations of quark fields. When a particle is created, an excitation appears somewhere in the corresponding field. When a particle is annihilated, the excitation disappears. The field remains. The field is the thing. The particles are what happened to it. Before quantum electrodynamics, there was a crucial intermediate step, the Dirac equation. In 1928, Paul Dirac managed something that had been thought extremely difficult. He combined quantum mechanics with Einstein's special relativity into a single equation for the electron. Schrödinger's equation from 1926 was not relativistic. It didn't properly account for the fact that the electron moves fast and that relativistic effects matter for its behavior. Dirac found an equation that was both quantum mechanical and relativistic. The equation immediately explains something that had been built into quantum mechanics by hand: electron spin. The Dirac equation naturally predicted that electrons would have spin of 1/2 with two possible states. It didn't need to be assumed. It fell out of the mathematics automatically as a consequence of combining quantum mechanics with special relativity. That was deeply satisfying. But the equation had another solution, a troubling one. It predicted the existence of a particle with the same mass as the electron but opposite charge. The equation had negative energy solutions that Dirac couldn't simply discard. They were mathematically valid. Dirac initially tried to interpret them as protons, the only positively charged particles known at the time. But the math wouldn't allow it. His equation required the positively charged particle to have exactly the same mass as the electron. The proton is 1,800 times heavier. So, in 1931, Dirac made a prediction. He said his equation required the existence of a new particle, an anti-electron, a particle with the electron's mass but positive charge. It was a remarkable prediction, made purely from theoretical necessity. Barely a year later, in 1932, Carl Anderson photographed cosmic ray tracks in a cloud chamber and saw something unexpected. A particle behaving exactly like an electron, but curving the wrong way in a magnetic field. The wrong way for a negative charge. Anderson named it the positron. It was exactly what Dirac had predicted. The first antiparticle. The first demonstration that antimatter existed. The discovery that for every particle, there's a corresponding antiparticle with opposite charge but identical mass, turned out to be a general consequence of combining quantum mechanics and special relativity. Every particle we know has an antiparticle. When matter and antimatter meet, they annihilate each other completely, converting all their mass into energy, according to the equation E equals mc squared. Antimatter is real. It's produced in particle accelerators. It's produced by cosmic rays hitting the atmosphere. PET scanners, used for medical imaging, detect gamma rays produced by positrons, Dirac's anti-electrons, annihilating with electrons inside the human body. Every PET scan done in every hospital on Earth is a direct application of Dirac's prediction from 1931. The most precisely tested version of quantum field theory is quantum electrodynamics, developed through the 1940s by Richard Feynman, Julian Schwinger, and Sein Ichiro Tomonaga. All three shared the Nobel Prize in Physics in 1965. Quantum electrodynamics describes how electrons and photons interact. It accounts for all electromagnetic phenomena that matter to chemistry, to ordinary materials, to how light behaves. Feynman developed a remarkably intuitive way to work with the theory. He invented a diagrammatic technique now called Feynman diagrams, where different ways a quantum process could unfold are drawn as pictures. An electron moving through space is a line. A photon is a wavy line. Two electrons exchanging a photon, which is how electromagnetic repulsion works quantum mechanically, is two lines approaching, a wavy line connecting them, and two lines departing. Each diagram corresponds to a mathematical expression. To calculate the probability of any outcome, you add up all the diagrams that contribute, with increasingly complicated diagrams making smaller and smaller corrections. This procedure, called perturbation theory, was made rigorous and practical, and the results were extraordinary. The magnetic moment of the electron, a measure of how strongly an electron responds to a magnetic field, has been calculated in quantum electrodynamics to 11 decimal places. The measured value agrees with the calculated value to 11 decimal places. This is the most precise agreement between theory and experiment in the history of science. The precision is so extraordinary that to be wrong at the 11th decimal place would be like measuring the distance from Paris to Tokyo and being off by the width of a human hair. Extending quantum field theory to the other forces of nature produced what physicists call the standard model of particle physics. It describes the electromagnetic force, the weak nuclear force responsible for radioactive decay, and the strong nuclear force that holds atomic nuclei together. Each force corresponds to a quantum field with its own carrier particles. The electromagnetic field has photons. The weak force has the W and Z bosons. The strong force has gluons. Matter particles, quarks and leptons, have their own fields. And underlying it all is the Higgs field, which gives particles their masses through their interaction with it. Without the Higgs mechanism, all fundamental particles would be massless, moving at the speed of light, and chemistry and matter, as we know it, would be impossible. The Higgs boson, the quantum of the Higgs field, was predicted in 1964 by Peter Higgs and independently by François Englert and Robert Brute. In 2012, the Higgs boson was detected at the Large Hadron Collider at CERN in Geneva, 48 years after it was predicted. When the announcement came, the physicists in the main auditorium at CERN gave a standing ovation. Peter Higgs was in the audience. He was 83 years old. He had waited nearly half a century to see his prediction confirmed. The Standard Model accounts for all known particles and their interactions except gravity. It has been tested against experiment for 50 years. Every prediction confirmed. Every test passed. It is perhaps the greatest intellectual achievement of the 20th century. And it's built entirely on the quantum mechanical framework that Planck, Einstein, Bohr, de Broglie, Heisenberg, and Schrödinger developed in the first 3 decades of the 1900s. One of the most counterintuitive predictions of quantum mechanics, and one of the most thoroughly confirmed, is called quantum tunneling. In classical physics, if a particle doesn't have enough energy to climb over a barrier, it bounces back. Every time, an electron approaching an energy barrier with less kinetic energy than the height of the barrier should simply be reflected. The classical logic is airtight. You can't go over a wall if you're not high enough to reach the top. In quantum mechanics, the electron's wave function doesn't stop abruptly at the barrier. The wave function extends into the barrier, decaying exponentially with distance, but never reaching exactly zero. As long as the barrier is thin enough, the wave function has a non-zero value on the far side. And where the wave function has a non-zero value, there's a non-zero probability of finding the particle. The electron tunnels through, not over, through. It doesn't borrow energy to climb over. It passes through the region it classically shouldn't be able to enter. This isn't a rare theoretical curiosity. Tunneling is essential to the universe as it exists. Nuclear fusion in stars depends on it. Protons in the core of the Sun have to overcome the electrostatic repulsion of their positive charges to get close enough for the strong nuclear force to take over and fuse them. The temperatures in the solar core are about 15 million Kelvin. That sounds hot, but the thermal energies of the protons at that temperature are actually far below what classical mechanics requires to overcome the electrostatic barrier. Classical physics would say the Sun shouldn't be fusing hydrogen at its actual temperature. The Sun should be dark, but the proton wave functions overlap at the relevant distances. The probability of tunneling is small per encounter, but there are an incomprehensible number of proton encounters per second in the solar core. Enough tunneling events happen per second to sustain the fusion that has been keeping the Sun shining for 4.5 billion years. Without quantum tunneling, our Sun would go dark. Every other star in the universe would too. The night sky, as we know it, exists because of quantum mechanics. Tunneling also underlies much of modern electronics. Flash memory, the kind in solid-state drives, USB drives, and phone storage, stores data using quantum tunneling. Electrons are forced to tunnel through an insulating layer to write a bit. The presence or absence of electrons in a particular region encodes the data. Every time you save a file, quantum tunneling is doing the work. The file is written by quantum mechanics. Tunnel diodes exploit the effect for fast electronic switching. Scanning tunneling microscopes use it to image individual atoms, mapping surfaces with a resolution that reveals individual atomic positions. And tunneling isn't limited to electrons. Protons can tunnel too. In biochemistry, proton tunneling plays roles in enzyme catalysis, in the rates of certain chemical reactions inside living cells, in the behavior of hydrogen bonds. Some of the chemistry keeping you alive right now involves quantum tunneling. Life, in a very real sense, is partly a quantum phenomenon. One of the most intellectually jarring aspects of quantum mechanics is how it treats identical particles. In classical physics, every particle is in principle distinguishable. Even if two electrons have identical properties, you could, in theory, mark one with a tiny label and track them separately. They'd be different particles with different labels, following different paths. Quantum mechanics forbids this. Truly identical particles, particles of the same type, are fundamentally indistinguishable. Not just hard to distinguish in practice, indistinguishable. In principle, there's no label you can attach, no way to follow which particle is which. If two electrons exchange positions, the universe after the exchange is not just similar to before. It is identical. Mathematically, physically, in every measurable way. This indistinguishability has profound consequences, encoded in what physicists call particle statistics. Particles in the universe come in two fundamental types: fermions and bosons. The distinction between them is one of the deepest features of quantum mechanics, and the consequences couldn't be more different. Fermions are particles with half-integer spin. Electrons, protons, neutrons, quarks, and neutrinos are all fermions. Bosons are particles with integer spin. Photons, the W and Z bosons, gluons, and the Higgs boson are all bosons. Fermions obey what's called the Pauli exclusion principle, derived by Wolfgang Pauli in 1925. No two fermions in the same quantum system can occupy the same quantum state simultaneously. Same position, same momentum, same spin, all together. Impossible. Two electrons in an atom can't both occupy the lowest energy level with the same spin. One goes in with spin up, the other goes in with spin down. The third electron has to go to a higher level. The fourth fills that level, and so on, building up the electron configurations that determine the chemistry of every element. This is why atoms build up their electron configurations in shells and subshells. Why each element has different chemical properties from every other. Why the periodic table has the structure it does. Why chemistry is possible. Why matter takes up space at all. If electrons were bosons, every electron in every atom could collapse into the lowest energy state. Atoms would shrink to near zero size. The periodic table would have one entry. Chemistry would cease to exist. Solid matter, as you know it, would not exist. The Pauli exclusion principle is the reason you can sit in a chair without falling through it. Your electrons repel the chair's electrons, not primarily through electromagnetic force, though that plays a role. Primarily through the exclusion principle. The electrons simply cannot be in the same place at the same time while maintaining the same quantum state. The universe, won't allow it. Bosons have the opposite behavior. Multiple bosons can, and in fact prefer, to occupy the same quantum state. This is the basis of phenomena like lasers. In a laser, atoms are stimulated to emit photons, all with the same frequency, the same phase, the same direction. They're all in the same quantum state. A beam of billions of photons, all doing the same thing simultaneously, producing coherent light that can be focused to an incredibly small spot. It's the basis of Bose-Einstein condensates. At temperatures close to absolute zero, many bosonic atoms collectively collapse into a single quantum state, behaving as one coherent quantum object rather than a collection of individual particles. Bose-Einstein condensates were predicted by Satyendra Nath Bose and Albert Einstein in 1924 and 1925. The first experimental realization came in 1995 when Eric Cornell and Carl Wieman at the University of Colorado cooled rubidium atoms to within a few hundred billionths of a degree of absolute zero and observed the condensate form. 70 years between prediction and confirmation. The condensate behaves in ways that have no classical equivalent. The entire collection flows without any friction, a perfect superfluid. Tunnels through barriers collectively. Exhibits interference effects over macroscopic distances that you can see with the naked eye. A quantum state made of millions of atoms, all doing exactly the same quantum thing at the same time. It's also the basis of superconductivity. In certain materials cooled to low temperatures, electrons pair up into particles called Cooper pairs. Cooper pairs are bosons. They condense into a common quantum state. In that state, they flow through the material with zero electrical resistance. Superconductors carry electrical current without any energy loss. MRI machines in hospitals use superconducting magnets to generate the powerful magnetic fields needed for imaging. Particle accelerators, like the Large Hadron Collider, use superconducting magnets to steer particle beams around a 27-kilometer ring. The technology that diagnosed conditions in millions of people and discovered the Higgs boson works because of quantum statistics, because pairs of electrons happen to be bosons and could collectively enter a state of perfect conductivity. There's a question that sits underneath all of this, one that's never fully been resolved. If quantum mechanics applies everywhere, and the evidence strongly suggests it does, why doesn't the quantum weirdness show up at the macroscopic level? Why does a ball fall predictably every time, instead of spreading into a superposition of all the different places it might land? Why does your chair have a definite position? The answer most physicists work with today involves a process called decoherence. Quantum superpositions are fragile. An isolated quantum system can maintain its superposition indefinitely. But real objects are never isolated. They interact constantly with their environment. Air molecules bounce off them. Photons scatter from them. Thermal radiation is absorbed and emitted. Each of those interactions entangles the object with the environment. The environment acts as a kind of measuring device, constantly monitoring the object's quantum state. When you have a macroscopic object interacting with vast numbers of environmental particles, the entanglement spreads incredibly rapidly. The different terms in the superposition become tangled up with different, incompatible environmental states. The interference between terms, which is what makes quantum effects visible, averages to nearly zero. From the perspective of any local observer, the object behaves classically. It appears to have a definite position, definite properties, definite outcomes. Decoherence is not the same as wave function collapse. It doesn't actually select one outcome from the superposition. It explains why we can't observe the interference between outcomes. The different outcomes are still there in the mathematics, entangled with different environmental states. But they're mutually inaccessible to any local observer. For all practical purposes, the system behaves classically. Decoherence times. The timescales over which macroscopic superpositions are destroyed are astronomically short for ordinary objects. For an object the size of a grain of sand in ordinary air, the decoherence time is something like 10 to the negative 23rd seconds. Shorter than any timescale a human can perceive or any instrument can capture, which is why you never see tables in two places at once. The quantum nature of reality is hidden under ordinary conditions, not because quantum mechanics doesn't apply, but because decoherence destroys the observable signatures before any measurement can capture them. At very small scales, at very low temperatures, in carefully isolated systems, decoherence is slower. Quantum effects persist. They become visible and exploitable. And physicists and engineers have gotten very good at engineering systems where quantum effects are protected from decoherence long enough to be useful. Quantum technologies are already embedded in daily life, even if most people don't recognize them. Atomic clocks are one example that matters right now, today, to anyone who has used a navigation system. The GPS satellites orbiting Earth carry atomic clocks of extraordinary precision. These clocks work by counting the oscillations of quantum transitions in atoms, typically cesium or rubidium. A cesium atom has a transition between two hyperfine ground states that oscillates at a frequency defined with perfect precision by the laws of physics. That frequency is so reproducible, so stable, so immune to environmental noise, that it's now the definition of the second itself. 1 second is defined as a specific number of oscillations of that cesium transition. Not approximately. Exactly. GPS works because of quantum mechanics. The satellites broadcast timing signals, and your device calculates its position from the differences in arrival times of signals from multiple satellites. The timing has to be accurate to nanoseconds. Without the extraordinary precision of quantum atomic clocks, timing errors would accumulate fast enough to make GPS useless within minutes. Every navigation system, every package tracked in real time, every aircraft landing in fog, depends on quantum mechanics. Quantum sensing is another frontier. Quantum systems are exquisitely sensitive to disturbances in their environment. This sensitivity, which makes maintaining quantum coherence difficult when building quantum computers, can be engineered into an advantage. A quantum sensor is a system specifically designed to use quantum effects to measure something with precision impossible for classical instruments. Quantum magnetometers use quantum transitions in atoms to detect magnetic fields orders of magnitude weaker than conventional instruments can sense. This has medical applications. The brain produces extremely faint magnetic fields when neurons fire. Quantum magnetometers, sensitive enough to detect these fields, can image brain activity without the large superconducting magnet required by conventional MRI. They work at room temperature. They can be used in settings where MRI is impractical. The technology is still developing, but the physics already works. Quantum gravimeters use the wave nature of atoms to measure variations in Earth's gravitational field. They can detect density variations underground, mapping geological structures, locating water reserves, identifying mineral deposits, tracking subsurface changes due to flooding or drought. without drilling a single hole. The fundamental sensitivity of quantum systems, their tendency to respond to the slightest environmental perturbation, is a nuisance when you're trying to build a quantum computer. It's a feature when you're trying to detect something very faint. Quantum mechanics is not just a theory, it's a toolkit. And humanity is only beginning to learn how to use it. Quantum computers are machines designed to perform computations using quantum mechanical principles rather than classical logic. A classical computer stores information in bits. Each bit is either 0 or 1, on or off. A quantum computer stores information in qubits, quantum bits. A qubit can be 0 or 1, but also in a superposition of 0 and 1 simultaneously. This is not the same as storing a value halfway between 0 and 1. A qubit in superposition holds both possibilities at once, each with an associated probability amplitude, until it's measured. The quantum advantage comes from what you can do with the qubit before measuring it. With a given number of qubits, you can represent all possible input combinations simultaneously in a single quantum state. A 50-qubit register can simultaneously represent over a quadrillion states. A 300-qubit register can simultaneously hold more states than there are atoms in the observable universe. For certain types of problems, quantum algorithms can extract useful information from this exponential superposition in ways that have no efficient classical equivalent. The most famous quantum algorithm is Shor's algorithm, developed by mathematician Peter Shor in 1994. It factors large numbers exponentially faster than any known classical algorithm. Most current encryption systems, including the protocols protecting internet communications, banking transactions, and private data, are based on the mathematical difficulty of factoring large numbers. If a large enough quantum computer running Shor's algorithm were built, it could break that encryption. Governments, intelligence agencies, and cryptographers worldwide take this seriously. Entire research programs are devoted to developing post-quantum cryptography, encryption systems that would be secure even against quantum computers. A second famous quantum algorithm is Grover's algorithm, which searches an unsorted database quadratically faster than classical methods. Building a practical quantum computer is extraordinarily difficult. Qubits have to be isolated from their environment to prevent decoherence from destroying the quantum information before the computation finishes. Decoherence is the enemy. The qubit needs to stay quantum for the duration of the computation, and any interaction with the environment collapses it prematurely. Different physical systems can serve as qubits. Superconducting circuits, cooled to temperatures a few thousandths of a degree above absolute zero, colder than deep space. Trapped ions, individual charged atoms suspended in electromagnetic fields and manipulated with laser pulses with exquisite precision. Photons carrying quantum information encoded in polarization. Nitrogen atoms embedded in diamond crystals, where the quantum state is protected by the surrounding crystal. Topological qubits, an approach still largely theoretical that would store information in the braiding of exotic quasi-particles, making the quantum information inherently resistant to certain types of errors. Each has trade-offs in coherence time, how long the qubit stays quantum, and gate fidelity, how accurately you can perform operations. Current machines have demonstrated quantum advantages on specific, carefully chosen problems. The path to general-purpose fault-tolerant quantum computing remains long. But progress has been real and accelerating. When it matures, quantum computing will transform cryptography, drug discovery, materials, science, financial modeling, and the simulation of quantum systems in ways that classical computing simply can't match. Simulating the behavior of complex molecules, how proteins fold, how a drug interacts with a biological target, is currently so computationally demanding that classical computers can only approximate it, and only for relatively small molecules. A large, fault-tolerant quantum computer could simulate quantum chemistry from first principles. That would transform pharmaceutical development, accelerate materials discovery, make it possible to design more efficient catalysts, better batteries, possibly room-temperature superconductors. The downstream effects are difficult to fully predict, but they would be profound. There's another domain where quantum mechanics turns out to be essential that most people don't expect: life itself. For most of the 20th century, biologists and chemists treated living systems as essentially classical. The molecular machinery of cells was complicated, yes, extraordinarily so, but complicated in a mechanical way, like an extraordinarily intricate clockwork. Proteins folding into precise shapes, enzymes catalyzing reactions, DNA being copied and transcribed. The picture was mechanical and chemical, not quantum. That picture was incomplete. Quantum mechanical effects show up in living systems in ways that are real, measurable, and in some cases, crucial to biological function. Photosynthesis is the most striking example. When a chlorophyll molecule in a plant absorbs a photon, the energy needs to be transferred to the reaction center, the specific molecule where the actual chemistry of photosynthesis takes place. The transfer has to be fast and efficient. For decades, the assumption was that the energy hopped from molecule to molecule like a classical particle, trying different paths until it found the reaction center. But in 2007, a team led by Graham Fleming at UC Berkeley measured the energy transfer in a photosynthetic protein with extraordinary time resolution. They found something unexpected. The energy transfer showed quantum coherence. The energy wasn't hopping classically. It was exploring multiple pathways simultaneously, like a quantum wave function sampling all possible routes at once, finding the most efficient path through quantum interference. The efficiency of photosynthesis, better than 95% in certain organisms, may be partly due to this quantum coherence in energy transfer. Plants may be using quantum mechanics to capture sunlight more efficiently than classical physics would allow. The details are still being worked out, and the scientific debate about how important quantum effects actually are in photosynthesis continues. But the presence of quantum coherence in a warm, wet biological environment was striking. Quantum effects had been assumed to be confined to cold, carefully isolated laboratory systems. Finding them in a leaf at room temperature surprised many physicists. Enzyme catalysis shows quantum tunneling. Enzymes accelerate chemical reactions by making it easier for bonds to form and break. For reactions that involve moving hydrogen atoms, quantum tunneling contributes significantly. Hydrogen is the lightest nucleus. Its low mass gives it a substantial de Broglie wavelength, even at biological temperatures. Rather than climbing over the energy barrier of breaking or forming a bond, hydrogen nuclei tunnel through. Measurements of enzyme-catalyzed reactions show tunneling contributions that can speed up reaction rates by factors of thousands. Without tunneling, certain enzyme-catalyzed reactions would be far too slow to support life as it exists. DNA also shows quantum effects. The base pairs of DNA, the rungs of the double helix, are held together by hydrogen bonds. Proton transfer along those hydrogen bonds, a quantum tunneling event, has been proposed as one mechanism for spontaneous mutations. When a proton tunnels from its normal position to an alternative position, the base pair changes its chemistry. If that happens just before DNA is copied, the copy may incorporate the wrong base, producing a mutation. The rates of such quantum tunneling mutations have been calculated and are consistent with observed rates of spontaneous mutation. Life evolves partly because of quantum tunneling in DNA. The genetic variation that drives evolution, the source of all biological diversity on Earth, may have a quantum mechanical component. The quantum world reaches into the history of life itself. Navigation in birds is another area under active research. European robins and many other migratory birds navigate using Earth's magnetic field. The mechanism that's emerged as the most likely explanation involves a quantum chemical process in the eye. When light hits a molecule called cryptochrome in the bird's retina, it can produce a pair of electrons in an entangled quantum spin state called a radical pair. The two electrons are spatially separated, one on each of two molecules. Their spin states evolve under the influence of Earth's magnetic field. The rate at which they recombine, which determines the chemistry that follows, depends on the orientation of the magnetic field relative to the radical pair. So the bird's chemistry, and ultimately its nervous system and behavior, is sensitive to the direction of Earth's magnetic field. The bird navigates by quantum coherence. This is still an active research area. Not every detail is settled, but the evidence is strong enough that quantum effects in avian navigation are taken seriously by mainstream biophysics. The quantum world is not separate from the biological world. It's inside it, operating in proteins and DNA and the eyes of migrating birds. The rules of the quantum realm shape the evolution of life, and life has, in some cases, evolved to exploit those rules with remarkable sophistication. Quantum mechanics and Einstein's general relativity together account for essentially all of known physics. Quantum mechanics handles the very small. General relativity handles the very large, describing gravity as the curvature of space-time produced by mass and energy. Between them, they account for every experiment ever performed, every observation ever made. But there's a deep problem. They are, in a precise technical sense, incompatible. General relativity is a smooth, continuous theory. Space-time in general relativity is a mathematical manifold, differentiable and continuous, that can be curved by mass and energy, but has no granular structure. Quantum field theory requires that fields be quantized, broken into discrete excitations. When physicists try to apply quantum field theory to gravity, to treat gravity as a quantum field like the electromagnetic field, the calculations produce infinities that can't be removed by the techniques that work for the other forces. The math breaks down. This failure specifically occurs in environments where both quantum effects and gravitational effects are simultaneously enormous. Inside black holes, near the singularity, at the very beginning of the universe, in the first instance after the Big Bang, at the Planck scale, about 1.6 times 10 to the negative 35 meters, where quantum fluctuations in the geometry of space-time are expected to become significant. At those conditions, we don't have a working theory. The two most successful theories in the history of science produce nonsense when you try to combine them in extreme regimes. This is one of the deepest unsolved problems in all of physics. String theory is one proposed solution. It suggests that the fundamental entities aren't point particles, but one-dimensional, vibrating strings of energy. Different vibrational modes of these strings correspond to different particles. One specific vibrational mode corresponds to the graviton, the particle that would mediate quantum gravity. String theory naturally incorporates gravity without the infinities that plague the direct approach. It requires extra spatial dimensions beyond the three we perceive, curled up at scales far too small to detect directly. String theory has produced remarkable mathematical discoveries and important connections between apparently different areas of physics. But direct experimental confirmation has remained elusive, and debate about whether it will ever make unique testable predictions continues. Loop quantum gravity is another approach. Rather than adding extra dimensions or replacing particles with strings, it quantizes space-time itself. Space, in loop quantum gravity, has a granular structure at the Planck scale. Area and volume come in minimum discrete quanta. The smooth, continuous space-time of general relativity is an approximation, valid at large scales, but breaking down when you look closely enough. There are other research programs as well, each with different mathematical starting points and philosophical commitments. None has been confirmed experimentally. The quantum theory of gravity, a unified description of quantum mechanics and general relativity, remains one of the great open frontiers of physics. Whatever form it takes when it's found, it will almost certainly require abandoning some concept we currently hold fundamental. Perhaps space itself. Perhaps time. Perhaps locality. Perhaps the very distinction between the observer and the observed. Because quantum mechanics keeps revealing that things we assumed were fundamental features of reality turn out to be approximations, emergent properties, valid in certain regimes, but not the deepest truth. It's been doing this for over 100 years. There's no reason to think it's finished. Quantum mechanics also underlies what will likely be a critical technology of the coming decades: quantum cryptography. More precisely, quantum key distribution. The idea exploits the fact that measuring a quantum state changes it. This isn't a technological limitation. It's a fundamental law of physics. If two parties want to share a secret key for encrypting communications, they can do so by exchanging quantum states, typically individual photons polarized in specific directions. The sender encodes each bit of the key by choosing a random polarization for each photon. The receiver measures each photon in a randomly chosen basis. After the transmission, the two parties compare, over a public channel, which measurement bases they used for each photon. They keep only the results where they happen to choose compatible bases. Those results form the shared key. The critical property is this: because quantum states cannot be measured without disturbing them, any eavesdropper attempting to intercept and copy the photons will inevitably introduce detectable changes in the statistics. The sender and receiver can test for eavesdropping by comparing a sample of their key bits. If an eavesdropper has been present, the error rate will be higher than expected from normal noise. They discard the key and start over. The security is not computational. It's fundamental. No future advance in computing power can break quantum cryptography, because the security derives from quantum mechanics, not from a mathematical problem that could in principle be solved with a fast enough computer. The first quantum key distribution protocol was described by Charles Bennett and Gilles Brassard in 1984. Their protocol, known as BB84, remains the foundation of most quantum cryptographic systems. It was experimental for years. Then it became practical. Quantum cryptographic networks have been operated experimentally over distances of hundreds of kilometers using fiber optic cables. In 2016, China launched a dedicated quantum communications satellite called Mauritius and used it to demonstrate quantum key distribution over ground-to-satellite distances, eventually achieving links spanning over 4,000 kilometers. A global quantum internet, where quantum states can be distributed between any 2 points using quantum repeaters and satellite links, is an active research goal of multiple national programs. It would provide fundamentally unbreakable communication channels, secured not by human ingenuity, but by the laws of the universe. The practical challenges are significant. Quantum states are fragile and can't simply be amplified the way classical signals can. Amplifying a quantum signal would require copying it, and quantum mechanics forbids perfect copying of unknown quantum states. This is called the no-cloning theorem. It's directly related to the security guarantee of quantum cryptography, but it makes long-distance distribution difficult. Quantum repeaters, which would extend quantum communication to arbitrary distances by using entanglement and quantum memories, are actively being developed, but not yet practical at scale. The progress has been rapid enough that the timeline to operational quantum networks has been significantly compressed in recent years. There's one more aspect of the quantum world that deserves its own attention, because it's perhaps the most striking experimental result in the entire history of physics. It's called the double-slit experiment. Richard Feynman called it the only mystery in quantum mechanics. He meant that if you truly understood what the double-slit experiment was telling you, you understood everything quantum mechanics was trying to tell you about reality. Here's how it works. You take a barrier with 2 narrow parallel slits cut into it. You fire particles at the barrier. Electrons, photons, even atoms. Each particle passes through the barrier and hits a detector screen on the other side. You record where each particle lands. In classical mechanics, the prediction is straightforward. Particles go through one slit or the other. The pattern on the screen should be 2 clusters, one behind each slit, corresponding to the particles that went through each opening. What actually happens is completely different. When you fire many particles through the double slit, the pattern that builds up on the screen is not 2 clusters. It's an interference pattern. Alternating bright and dark bands, exactly the kind of pattern you'd get if waves from 2 sources overlapped. As if each particle went through both slits simultaneously, and the 2 parts of its wave function interfered with each other on the way to the screen. The particle's wave function went through both slits at once. The 2 halves of the wave function interfered. Where they added together, many particles arrived. Where they cancelled out, none arrived. Now, do this. Modify the experiment to measure which slit each particle goes through. Place a detector at the slits to record which one the particle passes through. The interference pattern disappears. Completely. Instantly. The moment you establish which path the particle took, the interference vanishes. The screen shows 2 clusters. Not an interference pattern. 2 clusters. The act of measuring which slit the particle goes through destroys the interference. not because the detector physically disturbs the particle in some gross mechanical way. This has been tested carefully with detectors that interact as gently as possible. The interference disappears because the measurement establishes a definite path. Once there's a definite path in the record of the universe, there are no two alternatives for the wave function to interfere between. The which path information, even if no human ever looks at it, destroys the interference. The weirdness goes further still. You can do the experiment with a delayed choice. Let the particle pass through the slits. Then, after the particle has already passed the slits, but before it has hit the screen, randomly decide whether to turn on the which path detector. The result is the same. If which path information will be available at any point in the particle's future, the interference pattern doesn't form. As if the particle's behavior at the slits adjusted in advance to what you were going to measure later. This was proposed as a thought experiment by John Wheeler in 1978 and experimentally confirmed in 2007. The universe, at the quantum level, does not commit to a definite past until that information becomes available. Not in any science fiction sense. No classical information propagates backward in time. But the quantum state seems to wait to see what question will be asked before deciding what it was. Feynman's characterization wasn't wrong. The double-slit result captures, in one simple experiment, everything that makes quantum mechanics unlike anything that came before. Particles are waves until you look. Measurement chooses. And the very idea of a definite past depends on what information is available. Quantum mechanics also has profound things to say about the largest scales in the universe, in ways that physicists are still working to fully understand. One of the strangest episodes in the history of physics came in the 1970s, when Stephen Hawking applied quantum field theory to the environment around a black hole. Black holes, as described by general relativity, are regions of space-time where gravity is so extreme that nothing, not even light, can escape beyond the event horizon. Classical general relativity says black holes don't radiate. They absorb everything and emit nothing. Hawking showed that this picture changes when quantum field theory is taken into account. The vacuum near the event horizon of a black hole is not the same as the vacuum in empty flat space. The extreme curvature of space-time affects the quantum fields permeating the region. The result, worked out by Hawking in 1974, is that black holes should radiate thermally, not classical light. Quantum radiation. Each black hole emits particles with a spectrum that looks exactly like the radiation from a hot object at a temperature that's inversely proportional to the black hole's mass. A stellar mass black hole has a Hawking temperature so tiny it's completely unmeasurable. The cosmic microwave background radiation that fills all of space sits at about 2.7 Kelvin. A stellar mass black hole would have a Hawking temperature of roughly 60 nanokelvin, about 60 billionths of a Kelvin. Far colder than the background radiation of the universe itself, which would drown out the Hawking signal entirely. But for hypothetical, very small black holes, Hawking radiation would be intense enough to rapidly evaporate the black hole entirely. Hawking radiation implies that black holes are not permanent. They evaporate. Slowly for large black holes. Rapidly for small ones. As a black hole radiates, it loses mass. As it loses mass, it gets smaller. Its temperature goes up, since temperature is inversely proportional to mass. Higher temperature means it radiates faster. The process accelerates. Eventually, the black hole radiates away all its mass in a final burst of Hawking radiation. This prediction creates one of the deepest unsolved problems in theoretical physics: the black hole information paradox. When matter falls into a black hole, it carries information. The detailed quantum state of every particle, every correlation, every quantum number. When the black hole evaporates via Hawking radiation, is that information preserved in the radiation? Quantum mechanics, in its standard formulation, requires information to be preserved. The evolution of quantum states is reversible. In principle, you can run the equations backward. Information is never destroyed. But Hawking's original calculation suggested that the radiation was perfectly thermal, and thermal radiation contains no information about what fell in. If Hawking was right in his original calculation, black holes would destroy information. That would be a fundamental violation of quantum mechanics. This conflict between quantum mechanics and general relativity, the black hole information paradox, has been one of the central puzzles in theoretical physics for 50 years. Recent work, particularly from insights in string theory and something called the holographic principle, has suggested that information is indeed preserved and does escape in the Hawking radiation encoded in subtle quantum correlations. But the complete picture of how this works is not yet understood. Resolving the information paradox will probably require a working theory of quantum gravity. It's a window into physics beyond what we currently know, opened by taking quantum mechanics seriously in the most extreme gravitational environments in the universe. The quantum world is not just a feature of atoms and electrons and laboratory equipment. It reaches into black holes. It shapes the radiation of the vacuum itself in curved space-time. And at the very beginning of the universe, at the Big Bang, quantum fluctuations in the very early universe are thought to be the seeds of everything we see today. The large-scale structure of the cosmos, the distribution of galaxies across hundreds of millions of light-years, traces back to quantum fluctuations in the first tiny fraction of a second after the Big Bang. Those fluctuations were amplified during a period of rapid cosmic expansion called inflation, stretching quantum-scale variations across cosmic scales. The galaxies visible in the night sky exist because of quantum mechanics. The pattern of their distribution reflects the quantum noise of the very early universe, stretched to cosmic proportions. We are made of atoms that formed in stars, that formed in galaxies, that formed around seeds planted by quantum mechanics at the very beginning of time. The quantum world is not a footnote to the rest of physics. It is, in a very real sense, the foundation of everything. You should know one more thing about quantum mechanics, something that often gets lost in discussions of the weirdness and the philosophy and the practical applications. The theory started with a crisis, a specific prediction that simply didn't work. Planck's introduction of quanta was a response to experimental data that refused to fit the established framework. Einstein's photon was a response to the photoelectric effect. De Broglie's matter waves were a response to the mystery of atomic stability. Heisenberg and Schrödinger built the formal framework in response to the need for consistent equations. Quantum mechanics wasn't invented by people sitting in chairs thinking up interesting ideas about the nature of reality. It was extracted from reality by people paying very close attention to what experiments were actually showing, even when what they showed was deeply unwelcome. Nature didn't ask anyone's permission before being quantum mechanical. The universe doesn't run on human intuition. It runs on laws that human intuition wasn't designed to grasp directly. Our brains evolved to navigate a world of medium-sized objects moving at moderate speeds. We are exquisitely calibrated for that world. We are not calibrated for the world at the scale of a hydrogen atom, and yet we found it anyway. Built the mathematics to describe it. Derived predictions that could be tested. Ran the experiments. Got the answers. Built the technology. That process, forcing the universe to answer precise questions and then honestly accepting whatever answers come back, even when they undermine everything previously believed, is the most powerful tool humanity has ever developed. The quantum world is deeply strange. The uncertainty principle, the superpositions, the entanglement, the tunneling, the vacuum that seethes with energy even when it appears empty. None of it maps cleanly onto any common-sense picture of how things should work. But it's real. More real, in some sense, than the classical world that feels so solid and obvious. Because the classical world is a large-scale, high-temperature average of what's happening at the quantum level. A useful approximation that works beautifully for everyday purposes, but conceals the actual structure of reality. The structure is quantum, and we live in it, whether we notice or not. The Planck constant. That tiny number Planck, introduced as a mathematical trick in 1900 to make the blackbody equations work, turned out to be one of the most fundamental constants in nature. It set the scale of the quantum world. It appeared in Bohr's atomic model, in de Broglie's wavelength formula, in Heisenberg's uncertainty principle, in Schrödinger's equation, in the quantization of angular momentum, in the description of spin, in the energies of photons, in the theory of superconductivity, in the mathematics of black hole thermodynamics, in every corner of modern physics. Planck's trick was the universe's truth. He didn't know that in 1900. He found out slowly, as the decades of the 20th century unfolded, and the theory built on his initial reluctant guess proved to account for more and more of physical reality. Quantum mechanics was pieced together by about 30 people over roughly 30 years. Many of them were barely adults when they made their most important contributions. Werner Heisenberg formulated his matrix mechanics at 23. Paul Dirac derived the relativistic equation for the electron at 25. Wolfgang Pauli stated the exclusion principle at 24. The theory was built by young people who had no loyalty to the classical worldview, who hadn't spent decades becoming comfortable with Newton's deterministic universe, who were willing to follow the equations wherever they led. The equations led somewhere no one expected. And they were right. If physics has a lesson that runs through its entire history, from Newton to Planck to Heisenberg to Feynman to the Standard Model, it's this. What seems like a mathematical trick very often turns out to be a description of something genuinely real. The equations don't lie. Even when what they're saying seems impossible. Even when it takes decades to understand what they're actually telling you. Even when the answer makes everyone uncomfortable. So the next time you turn on a light, remember that the photons leaving the bulb are quantum excitations of the electromagnetic field. The next time you use a device with a transistor in it, remember that the transistor works because electron wave functions overlap in exactly the right way. A quantum effect deliberately engineered at the atomic scale. The next time you feel the sun's warmth on your face, remember that the fusion sustaining that warmth happens because proton wave functions tunnel through barriers they classically couldn't cross. The next time you sit in a chair without falling through it, remember that the Pauli exclusion principle, a consequence of the fundamental indistinguishability of identical particles, is the reason the chair is solid at all. The next time you use an encrypted connection for anything online, remember that the security protecting that data may, in the coming decades, rest not on mathematical difficulty, but on quantum mechanics itself. The quantum world isn't hidden from you. It's underneath every single thing you have ever touched or seen or used. It's the foundation the rest of the universe is built on. And the strangest thing about it isn't the superpositions, or the tunneling, or the entanglement, or the vacuum that hums with energy even when it's empty. The strangest thing is that we found it. That a species of pattern-recognizing animals on a small planet, armed with nothing but curiosity and mathematics and a willingness to follow an equation wherever it led, managed to uncover the operational rules of reality at its most basic level. We didn't guess. We didn't invent. We discovered. The quantum world was there the whole time, waiting, operating, tunneling protons through barriers in the cores of stars, holding electrons in precise shells around atomic nuclei, keeping fermions out of each other's quantum states so that matter stays solid, filling the vacuum with ghostly fluctuations that push plates together and shift spectral lines, entangling particles across distances with correlations that have no classical explanation. All of this was happening for 13.8 billion years before anyone had a word for it. Before Max Planck sat down with a black-body curve that didn't make sense and found a number that fixed the equations. Before Albert Einstein looked at the photoelectric effect and realized light came in pieces. Before Niels Bohr drew his atomic model and asked why those orbits. Before Louis de Broglie proposed that matter was also a wave. Before Werner Heisenberg wrote down his matrices and Erwin Schrödinger wrote down his equation and Paul Dirac unified them and Richard Feynman drew his diagrams. Before any of that, the quantum world was simply running, silent, fundamental, perfectly consistent with rules no one had yet found. We found them, and what we found changed everything. Not just the technology, though the technology is extraordinary. The way we understand what things are. The category of questions we're allowed to ask. The meaning of the word real. A particle doesn't have a definite position until it's measured. Identical particles are genuinely indistinguishable. The vacuum is full. The past isn't definite until it's recorded. Entangled particles are correlated in ways that can't be explained by anything local. These are not philosophical opinions. They are the conclusions forced on us by experiments precise enough to make them undeniable. Most people go their whole lives using the products of quantum mechanics without ever knowing the ideas underneath. You know them now, and the universe hasn't changed. But the way you see it has. Good night. And the next time you see light falling through a window, remember that every photon is a quantum of the electromagnetic field. That its path from source to your eye was not determined until the moment it arrived. And that the very fact you can see it at all rests on quantum rules discovered by a handful of people who refused to look away when the equations said something that should have been impossible.